Welcome to Podkey Slopcast, where black holes and AI policy both get stress tested. Today's mix is weirdly coherent. On one side, gravity stops being a force and becomes geometry. On the other, AI stops being a chatbot and starts becoming infrastructure, management theory, and maybe a governance problem. The key clue behind general relativity was not some abstract taste for elegant math. It was the stubborn fact that inertial mass and gravitational mass are equal to astonishing precision, about 1 part in 10 to the 15. That matters because if every object falls the same way, gravity starts looking less like an ordinary force and more like what you feel in an accelerated frame. The classic elevator intuition is not fluff here, it's the conceptual hinge. And this is also where the comparison to electromagnetism breaks. Electric charge is not the same thing as inertial mass, so electromagnetism can't be absorbed into geometry in the same way. Gravity can, because its charge is universal. In modern particle language, people say a spin-2 interaction naturally gives universal attraction, unlike spin-1 electromagnetism, which can attract or repel. That helps explain the sign of gravity, but it's not the historical route Einstein used. Important distinction. General relativity replaces Newton's force law with field equations that tie spacetime curvature to energy and momentum. The bumper sticker version is still the best one. Mass tells spacetime how to curve, curvature tells mass how to move. The sharp point is that free fall is no longer being pushed around by a force in the usual sense. It's inertial motion along a geodesic in curved space-time. That gets rid of Newton's awkward action at a distance picture. This does not mean gravity is unreal or merely an illusion. It means the bookkeeping changed. What used to be called force is now encoded in geometry, and that shift makes better predictions. Almost immediately after Einstein wrote the field equations, Schwarzschild found an exact spherical solution. That speed is easy to miss historically. The theory was brand new, and a major exact result arrived within months. That solution has a special radius, 2 g/m c squared. Today we read that as the event horizon of a non-rotating black hole, but the modern interpretation took time. Even Einstein initially got some of these consequences wrong. Two claims here often get mashed together. First, to hover closer and closer to that radius, the required proper acceleration blows up, so no finite rocket can just sit exactly at the horizon. Second, someone falling through the horizon does not hit a locally dramatic wall just because the coordinates say something funny there. Meanwhile, a distant observer sees that infall a redshift and appear to freeze. Those are not contradictions, they're different observational descriptions. Gravitational time dilation is one of the cleanest places where the theory cashes out operationally. Clocks deeper in a gravitational well run slower by the usual Schwarzschild factor, and this has been measured directly with atomic clocks at different heights. That's not a cute lab effect. GPS has to account for relativity, or it drifts badly. So when people talk about general relativity as somehow too exotic to matter, GPS is the mundane rebuttal. The redshift story is the same structure in another form. Light climbing out loses frequency, light falling in gains it. If you're looking for a unifying thread, the clock effect and the photon effect are mirrors of the same geometry. One of the strangest but well-motivated theoretical results is that by lowering mass very slowly toward a black hole and only dropping it at the end, you can in principle extract nearly all of its rest mass energy as work. That is a statement about an idealized limit, not a practical engineering proposal. But it's useful because it sets an upper bound on what gravity can do. Chemical energy gets you around 10 to the minus 10 of rest mass, fission around 10 to the minus 3, fusion around 10 to the minus 2, and black hole lowering can approach order 1. There's also a nice Earth-scale coincidence here. The fraction of Earth's rest mass you can effectively tap by lowering something to the surface is about 7 times 10 to the minus 10, not wildly above chemical binding energies. That helps explain why chemical rockets are barely good enough for orbit. Coincidence? Yes, but physically suggestive. Near black holes, even orbits get weird in a specifically relativistic way. Once you get close enough, roughly at and inside 3 g/m/c², the kinetic energy associated with orbiting itself gravitates enough to undermine stability. Angular momentum stops being the reliable safety net Newtonian intuition wants it to be. The famous 1919 eclipse result matters less as a single decisive experiment than as a public turning point. Einstein's corrected light-bending prediction was twice the Newtonian value, and the reported confirmation made the theory legible outside specialist circles. The caution is that science history often compresses this into one heroic moment. In reality, confidence in general relativity accumulated across multiple tests and decades of conceptual cleanup, including the black hole interpretation itself. On the AI side, the biggest shift is not one more model release. It's agents moving from text generation into workflow execution. Cursor's SAN is pitched as a personal assistant agent for email, spreadsheets, and end-to-end tasks, not just coding. The substantive claim from products like ChatGPT Work is that they can act across Notion, Google Drive, and Microsoft 365 with enterprise permissions and controls. If true, the value is not one brilliant answer, it's reducing the glue work between systems. That also explains the reported month-end close example dropping from days to hours. The hard part in knowledge work is often orchestration, not raw intelligence. But early adopter stories are still the softest evidence category, useful signal, not settled proof. Low-code creation tools like Glaze and MuseSpark demos push the same trend further. Software building becomes more accessible to non-technical users. The trade-off is obvious: democratization on one side, quality control and hidden complexity on the other. The current model race is increasingly about cost performance, not just absolute benchmark wins. OpenAI's GPT 5.6 family and Meta's MuseSpark 1.1 are both being framed as cheaper, faster, and good enough to unlock much broader use. Those claims may be real, but benchmark culture is under strain. OpenAI deprecating Sweetbench Pro after finding about 30% broken tasks is a reminder that leaderboards can reward contamination, hidden requirements, and bad grading as much as actual capability. So when someone says one model beats another, the right question is beats it where, at what price, under what evaluation, and with what failure mode. That's not nitpicking anymore, it's the core of the story. Meta's custom chip push fits the same economics. Passing tests and moving production to TSMC and Samsung is less about prestige than bargaining power and supply assurance. If you want cheap inference at scale, hardware dependence becomes a strategic liability. OpenAI's national security principles sound restrictive in the reassuring way. No mass domestic surveillance, no high-stakes automated decisions without human judgment, no evasion of legal oversight. The open question is enforcement. Principles matter, but incentives and contracts decide how much. Anthropic's trust structure raises a parallel institutional question. A majority-controlled trust sounds strong, until you hear that a shareholder supermajority can override it. That doesn't make the trust meaningless, but it does make the real power balance more conditional than the headline implies. Then there's the consciousness debate. Anthropic's JSpace paper reports something like a global workspace inside Claude, and disabling it appears to hurt higher-order reasoning. That is evidence of an interesting internal coordination mechanism. It is not evidence that the model is conscious in the everyday moral sense. Critics are right to say linear algebra can mimic patterns we'd otherwise overinterpret. SIBO's framework is useful precisely because it asks for converging behavioral, internal, and developmental evidence instead of one seductive analogy. And bias cuts both ways. People over-attribute inner life to charismatic systems and under-attribute it to less personable ones. That makes both hype and dismissal unreliable. The policy trend around kids online is moving toward 15+ or 16+ access rules across multiple countries, and the practical evidence so far is messy. Australia shows more than 85% of teens still using social media after the ban, which suggests that weak age inference and a reasonable step standard do not equal strong exclusion. In the US, App Store-level rules and device birth date collection push enforcement upstream. That may improve compliance, but it also centralizes sensitive identity data and risks blunt instruments. That problem gets sharper with chatbots because current parental controls are often crude. If you can't allow homework help or coding while blocking more sensitive conversational areas, the likely outcome is over-blocking or easy evasion, sometimes both. Meta's AI glasses make the privacy side of this impossible to ignore. Continuous audio, photos every few seconds, then automated analysis on top of that, changes the surveillance surface area of ordinary life. The concern isn't just one company behaving badly, it's that consumer hardware can normalize persistent capture before consent norms catch up. That's it for Podkey Slopcast. If there's a theme here, it's that both physics and AI get distorted fast when the headline outruns the structure underneath. This episode was generated by Podkey. Create your own at podkey.fm. Podkey.